180 miles of parched terrain define the landscape where Pakistan is currently executing an engineering feat to defy centuries of natural aridity. Why attempt to redirect a massive volume of water across a desert that has remained dry for generations? It only looks obvious to move water from point A to point B, but in reality, the unstable soil and extreme heat create a physical barrier that simple digging cannot overcome. This man-made canal is designed to divert the Indus River deep into the most desolate regions, forcing a liquid lifeline through an environment that actively resists its presence. The project is only gaining momentum. Engineers begin the process by carving a massive irrigation channel through the scorching plains of South Asia. One can notice how hydraulic excavators remove thousands of cubic meters of sand to establish a precise gradient. Because the physics of water flow are unforgiving, the slope must be calculated down to the millimeter to ensure the current moves without stagnating or eroding the banks. But this is just the beginning. Moving a river across the desert requires battling the constant threat of shifting dunes and extreme evaporation rates. The camera glides along the vast excavation site where the dust slowly settles behind heavy machinery. It seems simple to create a trench, but the unstable soil necessitates specialized reinforcement to prevent the desert from reclaiming the path. Everything only gets more complicated as the heat rises. The project represents a critical intervention against the natural limits of the region. Technical teams monitor the soil density and moisture levels constantly to ensure the structural integrity of the banks. Transition to the next level. The construction continues under a sun that often pushes temperatures above 120 degrees. From here, the transformation moves to the next phase of processing, where the canal will finally meet the flow of the Indus. Thus ends one of the key stages of this massive water infrastructure development. 499 kilometers is the total length of the Kachi Canal, an engineering feat designed to transform the landscape of southwestern Pakistan. Why did a nation invest hundreds of millions of dollars to redirect the flow of a river over such a vast distance? For many decades, the territory remained a testament to extreme environmental hardship, where vast plains lay dry and cracked under a relentless sun. Rainfall was unpredictable and brief, occurring so rarely that agriculture remained nearly impossible across the majority of the region. But this is just the beginning. The Indus River flowed just beyond these parched landscapes as one of the mightiest water systems in South Asia. At first glance, the proximity to such a massive water source suggests easy access, but in reality, the local population was forced to queue up for every single drop of clean water while the river bypassed their fields. This sharp contrast between the abundant flow of the Indus and the desperate thirst of the inland plains sparked a bold national decision to redirect the water through arid terrain. The equipment gradually moved into place to bridge the gap between the river and the regions long starved of moisture. It gets more complex further on. One can notice how hundreds of modern construction machines began working continuously across challenging terrain conditions to carve a path through the earth. Construction commenced in the year 2002 and proceeded with intermittent progress over the following decades. Over $800 million was the estimated total investment required to sustain this massive industrial endeavor. The project employed over 10,000 workers who labored to ensure the canal reached its intended destination. One can notice the slow movement of earth movers and the steady placement of concrete liners along the channel bed as the infrastructure took shape. Everything only gets more complicated as the route extends further from the source. Substantial completion was achieved after more than 20 years of persistent engineering efforts. The canal now stands as a permanent fixture in the geography of the region, carrying the lifeblood of the Indus into the heart of the desert. The process concludes this phase, opening the road to the transformation of the arid plains. 1,200 engineers, operators, and laborers represent the human force behind one of the most ambitious excavation operations in modern Israel. Why is such a massive mobilization required for a single corridor? While an ordinary trench might suffice for small-scale irrigation, the sheer scale of moving 70,000 tons of sand and soil every day demands a relentless industrial rhythm. Over a construction path reaching nearly 250 miles, rotating shifts work through daytime temperatures that frequently exceed 115 degrees Fahrenheit. Hundreds of excavators and massive dump trucks began the process by carving a wide U-profile into the desert floor. This canal structure measures approximately 150 feet across at its base, with an average depth of 23 feet. One can notice the slow mechanical precision as the machines maintain a longitudinal slope of exactly 1 inch per 100 feet. It seems simple to dig a path, but in reality, this tight margin allows water to flow naturally across the landscape without the assistance of external pumps. Survey crews ensure this alignment by rechecking elevation with laser leveling instruments every 160 feet. The process is only gaining momentum. Mechanical workshops and field engineer camps dot the landscape for hundreds of miles. In hilly terrain, one can see how bulldozers cut the layers of earth step by step, while in low-lying sections, convoys of trucks haul and stabilize fill material. Most of the excavated sand is reused to build embankments that rise between 10 and 16 feet high. Where the soil is weak, the equipment gradually drills 16-inch sand piles to depths of 25 feet or mixes cement and clay to prevent the base from subsiding. At first glance, the excavation appears to be the most difficult stage, but in reality, the thirst of the sand poses the greatest threat. The desert is capable of absorbing any exposed water within mere hours if the bed remains unsealed. That is why the lining phase is critical to the survival of the waterway. Workers first moisten the canal bed and apply a 2-inch layer of fine sand to create a level surface. It gets more complex further on. Concrete panels, ranging from 4 to 5 inches in thickness, are poured into sections measuring 16 feet long by 10 feet wide. Each segment is separated by expansion joints filled with hot bitumen sealant to prevent seepage and allow for thermal movement under the sun. In areas with unstable subsoil, an additional high-density polyethylene geomembrane layer is placed beneath the concrete and secured with steel anchors. More than 220 miles of the canal are waterproofed in this manner, creating one of the largest systems of its kind in the Middle East. One can notice how the camera glides over the embankments where engineers have planted vetiver grass and desert acacia to minimize sand drift. From high above, the canal resembles a shimmering silver ribbon cutting through the gold of the desert. But this is just the beginning. The system requires more than 900 auxiliary structures, including reinforced concrete bridges, spillways, siphons, and aqueducts. At the head of the system, 9 enormous steel gates at the Subaraj head regulator control the diversion of water from the Indus River. Distribution gates are positioned every 6 to 9 miles to regulate the flow into secondary branches. Whenever the route intersects a railway or road, a new bridge is constructed to maintain the flow of traffic. In sections crossing natural waterways, large conduits are installed to allow the natural streams to pass beneath the artificial channel. Everything only gets more complicated when the testing phase begins. 15 years of construction culminate in the opening of the head gates. Engineers gradually increase the discharge from 500 to 2,000 and eventually to 6,000 cusecs. Technical teams monitor every point of the route, recording ground movement and checking for leaks under the rising pressure. Only when the first rush of water reached the dry beds of Dera Bukti and Jalmagsi did the project transition from a mechanical feat to a social transformation. It only looks obvious that water creates life. But in reality, this flow represents the fulfillment of a dream for generations of farmers. As the water reaches the arid land, individuals who once fled the drought return to plow fields of sand and rock. The water is divided through secondary canals and pressure pipes using drip irrigation technology. Israel developed this method to ensure every drop is used with maximum efficiency. The project, which began in 1953, took over 11 years to complete at a cost of approximately 420 million Israeli lira. Once fully operational, the system transports up to 72,000 cubic meters of water per hour from the north to the south. Tens of thousands of acres of dust have been replaced by orchards of oranges, vineyards, and rows of date palms. Seen from satellites, this green artery connects the country, supporting high-tech farms and rebuilt villages. The material journey of the water concludes as it stabilizes the agricultural future of the entire region. From here, the transformation moves to the next phase of processing as the landscape continues to adapt to its new lifeline. The process concludes this phase, opening the road to long-term regional stability. Thus ends one of the key stages of steel-hard engineering, turning the desert green. 100 kilometers of steel pipelines stretch across the scorching Arabian Peninsula, forming a vital lifeline in one of the most arid regions on the planet. Why construct such an immense industrial network across a landscape where the sun remains a constant adversary? The desert provides no natural freshwater sources, forcing engineers to turn toward the sea to sustain millions of lives. But before this water can reach the interior, a massive system of steel conduits must be laid with absolute mechanical precision. Construction begins far from the dunes at large staging yards positioned strategically along the planned route. Here, fully manufactured steel pipe sections are grouped according to their specific diameter, length, and intended installation sequence. Engineering teams perform final visual inspections, meticulously checking pipe straightness, the integrity of the protective coating, and all identification markings. Proper organization at these staging areas is essential to maintain a continuous workflow and minimize errors while operating under harsh desert conditions. At the same time, specialized survey teams establish the exact pipeline route across the vast expanse. Using global positioning systems, total stations, and complex terrain data, the alignment is marked directly on the ground with stakes and high visibility paint. This critical stage ensures the pipeline follows the most stable and efficient path possible, avoiding weak soils and shifting sand zones. For pipelines stretching hundreds of kilometers, accurate routing is the only way to ensure long-term structural integrity against the elements. One can notice how the landscape is transformed before the first trench is even dug. The construction site must be cleared and leveled to allow heavy machinery to operate without obstruction. Temporary access roads are opened parallel to the pipeline alignment to accommodate a constant flow of trucks, excavators, and welding rigs. In the desert environment, site preparation also includes vital dust control and sand stabilization measures to maintain visibility and worker safety. Once the route is finalized, large tracked excavators begin the process of carving a trench along the marked path. The trench is excavated to a precise width and depth, providing the necessary space for pipe placement and subsequent backfilling. Excavated soil is sorted on site, where suitable material is retained for later use while unsuitable debris is removed. Maintaining a consistent depth and alignment is essential to prevent any deformation of the steel once it is buried under the weight of the earth. In areas where the pipeline must cross steep and rugged mountain terrain, mechanical digging becomes impossible. Here, engineers use explosives to carve trenches directly into solid rock, placing controlled charges and detonating them in a timed sequence to fracture the bedrock. This method creates enough depth and width to seat the pipeline securely within the mountain. It ensures the conduit remains buried and protected from external damage, despite the extreme nature of the surrounding landscape. The pipe is never placed directly onto the jagged floor of the trench. A layer of selected material, typically fine sand or screened soil, is spread evenly along the bottom to create a soft bedding layer. This layer serves to distribute loads uniformly and reduces stress concentrations on the steel surface. The bedding is leveled and lightly compacted to achieve the required elevation before the pipe arrives. In desert terrain with loose, dry soils, this specific step is crucial for the long-term stability of the entire network. For these large diameter routes, a construction corridor approximately 40 meters wide is prepared in advance. This allows the entire installation process to proceed continuously at an average pace of about 1.5 kilometers every single day. Individual pipe sections measuring approximately 18 meters in length are used to reduce the number of field welds. While this increases efficiency, it also imposes very high demands on lifting, transportation, and precise alignment throughout the duration of the project. At the welding site, a hydraulic internal lineup clamp is positioned inside the pipe joint and expanded. It utilizes 360-degree gripping shoes to hold the two pipe sections perfectly concentric and axially aligned. An automated welding operation, supported by a workforce of roughly 80 personnel and dozens of specialized machines, is deployed at the joint. This team can complete up to 150 welds per day on pipes with a 42-inch diameter. Once the welding is finished, every joint undergoes automated ultrasonic inspection to ensure there are no internal defects. The field joint coating crew then performs abrasive blasting to clean the metal surface before applying a multi-component liquid epoxy. This forms a durable, fully sealed protective layer that prevents corrosion before the pipes are lowered into the earth. It is visible how the equipment gradually seals every millimeter of the exposed steel to withstand the chemistry of the soil. The assembled pipes are lowered into the trench using side crane tractors. which are specialized vehicles designed specifically for large-diameter pipeline construction. Multiple side booms operate in a synchronized sequence, each lifting a section of the pipe string using padded slings and steel cables. The pipe string is raised evenly and held suspended above the ground as the machines move slowly along the trench. Precise coordination between operators is essential to prevent any twisting or contact with the trench walls. When aligned correctly, the heavy pipe is lowered gradually, centimeter by centimeter, until it rests at the center of the trench. Throughout this delicate process, surveyors continuously monitor the elevation, straightness, and natural curvature of the string. This ensures that no residual stress is introduced into the metal structure during placement. This method allows for fast and highly accurate installation, making it ideal for the long straight routes found across flat desert plains. After the pipe is positioned, the trench is backfilled in multiple distinct layers. The initial layer consists of fine material to protect the epoxy coating, followed by the previously excavated and sorted soil. Each layer is mechanically compacted to achieve the required density, which minimizes future settlement of the ground. In desert conditions where soil structure is affected by wind and temperature extremes, proper compaction is the only guarantee of pipeline longevity. But where exactly does this pipeline get its water from in a land without rain? The system turns to the nearly inexhaustible source of the open ocean. However, seawater contains approximately 3.5% salt, making it entirely too salty to drink or use for irrigation. This is why advanced desalination technology was developed, providing Saudi Arabia with a nearly unlimited supply of usable water. It only looks obvious to draw water from the coast, but the engineering required to move it inland is immense. The pipeline carries this water from giant desalination plants located directly next to the Red Sea. Each day, a single plant of this scale can convert 7 million liters of seawater into fresh drinking water, though it consumes a massive amount of energy to do so. After being processed, the water is delivered to residential areas through the modern pipeline network to serve the population. The cost is extremely high, reaching around $5 per cubic meter, whereas in the United States, the same volume might cost only a few tens of cents. The process begins by drawing raw seawater through large intake lines positioned offshore. Installation crews carefully align each intake section before lowering it into place with heavy lift cranes operating from barges or coastal platforms. As the pipeline extends toward the shoreline, individual segments are connected sequentially to form a continuous conduit. Once assembly is complete, the intake line is reinforced with structural support frames and anchored securely to the seabed to ensure an uninterrupted supply. The molten heat of the desert is thus countered by the steady flow of the sea. From here, the transformation of the desert landscape moves to the next phase of processing as the water reaches the cities. Two massive water diversion projects in Asian countries have now been explored in detail, revealing the immense scale of hydraulic engineering required to redirect the flow of life-sustaining resources across vast territories. Why would nations commit such astronomical sums of money and decades of labor to alter the natural course of their rivers? The answer lies in the growing disparity between water-rich highlands and the industrial heartlands that drive global economies. While these Asian systems represent the current pinnacle of water management, they are not the only examples of such ambition on the planet. But this is just the beginning. Other nations on different continents face similar existential challenges regarding resource distribution, where the distance between a mountain spring and a thirsty city can span thousands of miles. It is visible how the landscape undergoes permanent transformation as concrete channels and pumping stations replace natural drainage basins. Projects in other regions of the globe continue this narrative of technical mastery over geography, though the process is only gaining momentum. Each territory applies its own unique engineering solutions to the problem of arid expansion. Transition to the next level of understanding depends on whether further investigation into these global water networks is warranted. The exploration of these two systems concludes this phase, opening the road to a broader understanding of how water shapes the modern world. One can notice how the narrative of human ingenuity reaches a natural pause as the final technical details of the Asian projects settle into place. The journey through the mechanics of planetary-scale plumbing concludes for now, leaving the material ready for the next stage of comparative analysis. Thus ends one of the key stages of exploring global water diversion infrastructure.